analysis, prefixes, we did vectors. And in theory, that was supposed to be a bit of review either from high school physics or physics 110. And obviously, everybody was at a different spot. We did vectors. Okay, hold on. And in theory, that was supposed to be. All right, there, that's paused now. Okay, sorry about that. So if you had some trouble with that, try not to get too freaked out. Just put in some time and do some reading, ask me questions in office hours, and we'll get you up to speed on anything that maybe you had trouble with. That said, I want to move on to chapter 2. Now, to be clear here, chapter 2 in workbook equals chapter 3 in the OpenStax textbook. Similarly, chapter 3 in the workbook equals chapter 2 in OpenStax text. After that, they're in good agreement. But so when I was writing this, we were using a different book, and things have changed over the years. We changed books. So it turns out there's going to be a little bit of confusion in chapters 2 and 3. So if you're ever not sure if I'm talking about chapter 2 in the workbook or chapter 2 in the textbook, just ask. Generally speaking, I'm going to refer to my workbook when I'm talking about chapters. All right. So, all right. That said, I was thinking about this. Chapter 2 is our first kind of real physics here. Chapter 2 in the workbook. We're going to be talking about one-dimensional motion. All right. So, to me, I was trying to think what is the most fundamental equations that I want you to take away, because I wanted to start with those. Let me get some different markers here. And I thought of these two. What is velocity to you? Does anybody have a definition for velocity? Okay, I heard meters per second. That's the units of velocity. I like that. Let's stick that in there.
Like the rate of change.
Rate of change, something like that. Rate of change in position is better than distance, it turns out. With respect to what? Yes, okay. And I thought, even though you probably already know this, I just want to point this out that it's a big deal, and we're going to use this in coding. We're going to use this basically for the rest of our physics careers too. If you're a mechanical engineer, oh my gosh, you're going to use this all the time. So obviously we don't want to have to write all these words all the time. Oh, well, I probably just gave it away. Is velocity a vector or not? Yes. Velocity is a vector, right? So what's the way that you would write rate of change with respect to time? I heard somebody say delta. That's good. That's approximately valid. What's another way to write it with calculus? Not d over dx, but close. So d over dx would be the rate of change with respect to position. So with respect to time, it would be ddt of. Now, different books use different symbols. Because we're going to be doing one-dimensional motion, I might start with the symbol x, right? Some people use the symbol r. Okay, either one of these. Now, as written, this is kind of confusing. Let me ask you something. Over here, velocity is a vector, is it not? If one side of the equation is a vector, what must be true about the other side of the equation? Must also be a vector. Is time a vector? So we can't get any vector out of this crap. So this must also be a vector. So sometimes in 3D space, right? In 3D space, we have X, Y, and Z. So you wouldn't want to use X here for 3D space. We might actually use R. Okay. And to be clear, a lot of times when we get to chapter 4 in the workbook, we're going to be using the R vector because we're going to have X in the I hat, Y in the J hat, etc. Now, wait a minute. I said if one side of the equation is a vector, the other side must also be a vector. Is that true for what I just wrote here? This isn't a vector. Is I hat a vector? What does the hat symbol mean when it's sitting on there? Unit what? So is it a vector?
Yes.
It's a special kind of, so this doesn't look like a vector equation at first until you remember, oh yeah, this means X to the right. It's got a size and a direction. So this actually is okay, right? It's a vector on one side. These are also vectors. So far, so good? Just kind of keep that in mind. Okay, if it's a vector on one side, we want it to be a vector on the other. All right. And then maybe what I'll do is I'll put the units here, just so it's units of meters per second. That way I have some space here. That's a fundamental one-dimensional motion equation. All right. I was coming to school. I was driving, 70 miles per hour. What was my velocity? No. You need a direction. All right. I'm just trying to lay that in here, trying to emphasize this again. Speed is not velocity. Just because you know somebody's speed doesn't mean you know their direction, right? And so you know my speed was 70 miles per hour, but you don't know what direction I was going. Maybe I was coming from outer. All right. Anyways, okay, so that's velocity. Great. Well, the other fundamental equation that I want you to think about is one for acceleration. What is the equivalent statement for acceleration? Okay. From these two statements, we can get a lot of work done. With respect to his WRT here. Jules, is that showing up okay on Zoom, the red? All right, thanks. All right. So what's the equivalent equation? Well, acceleration, we're probably going to use letter A. Notice, I don't know if you did any of the homework in chapter 1. I try to use capital A for area, lowercase a for acceleration, just to kind of keep them straight. What's this going to be? Okay, that's fine. I was going to try and write this first and then do that. So you're right. Somebody said that's one way to write it. Absolutely. Good. What's another way to write it based off this sentence?
D over dt over b.
Yeah. Looking good or not? Good, right? We got to be very particular about checking, do I need the vectors? Do I not? Do I need i's, j's, whatever? What are the units going to be? Yeah. Now, when you're looking at this, a lot of people do their calculus without ever thinking about units. Look at this equation here, this top one, right? X is usually a distance or a position or something that's measured in meters, right? These D's don't have any units, but dt, that's a small amount of time, that's seconds. So here you can see it again. You got meters per second, or meters per second squared. So far, so good on the units. You can use derivatives to check the units as well. All right, so far, so good. Now, some of you probably, well, some of you probably know a kinematics equation, right? These are sort of big definitions. Do any of you know any equations in kinematics?
X final equals X initial plus B initial.
I heard something like this.
1/2 A T squared.
I heard this equation, X final equals X initial plus B initial X times time. And maybe you didn't say the subscript's X or not. Did you say that? Did you just
I
say?
did not say the subject.
Okay, but I'm going to go ahead and put this on here because you guys are probably smart enough to figure out in some other chapter, maybe we'd use the letter Y. And then that way we can distinguish between problems that have a velocity in the X initial or a problem that has acceleration in the X initial versus Y. Okay with that? So that's why I'm going to force that. Do you have to have that memorized or not? How could you check? Look for it in there somewhere. You got those equations somewhere?
Yeah, it's in the middle.
Is it? I can't even find. Oh, there they are, right there. Okay, so those are some equations that you can see. So if you're worried about having to memorize that, now you know you don't have to. Now, an equation is really nice, but maybe we should actually understand. Look at this. Do you see any vectors in here? It looks totally different than what we just did. The other ones were all vector equations, and this one doesn't. So I want to clarify what these symbols mean and how this relates to the last problem, and maybe even derive it from what we know from these definitions. All right. So first off, one of the things that's super frustrating as a student is when we talk about vectors and how directions are important and how crucial it is to always write the I hats and J hats and always make sure you have a vector on one side and not on the other. Every single physics textbook I've ever seen immediately ignores the vectors for this chapter. Really, there should be an I hat on every single term here. Okay? Now I want you to think about this. Why did I put the I hat next to the V instead of after the T here? Why do you think I would have done that?
The B is a vector and T is a scalar.
Absolutely. The V is the vector and T is a scalar. Now, to be clear, we could have put it at the end, but I was just trying to emphasize why the I hat is here. What does V initial X mean? Well, let's work it through. What does V usually mean? Yeah, now here, it looks like it's not a vector, so you might think speed, but in this case, so we have the initial right there. And then here, the extra X that I just put in the X direction. That's all that X subscript means here. All right. So the subscript I is going to be initial. Now I know you guys are going to watch internet videos of other teachers and you're going to read books and stuff, maybe. We'll see. So it's important sometimes that I show you a different way of writing this. Sometimes they'll write it like this. Velocity at time 0 in the X direction. All right. So do you agree those are basically the same way of saying it? Now, because we all read different books these days and some people watch different YouTube videos, I feel like it's important to mention both of these things. All right. All right. Let's talk about X. What does X mean in this equation? Anybody? What is it?
The axis.
I mean this right here. Sorry, in this equation. So what does X initial mean here? Let me write that down here. Whoops, I just said what the I means, right? What does the X mean though? Position, not distance, not displacement, position. Okay, so that's the initial position. And then to be clear, in the X direction. So if you were coding like we did in lab last week, remember we would write the vectors as vec parenthesis X, Y, Z, right? This would just be the first number in the parentheses in the order triple. All right. All right. Take a guess. What's another way this is sometimes written if you had to base it off this, right? Yeah, sometimes they'll call this X subscript 0 or position in the horizontal direction at time 0. So far, so good? All right. X final. That's going to be final position. All right. Now, just so you know, I probably should have said this a few minutes ago. All this is written down for you already on page 30. Nope. Page is it? 21. So if you want to have a lot of these terms open on page 21, you can have that there. So I apologize for not saying that earlier. Too focused on the cameras and crap again. But we're going through it anyways here, so it doesn't hurt to write it down because that'll make it stick in your brain anyways. All right. Now it turns out, sorry for that distraction there, and sorry for not getting it to you on a timely manner. There's another way many textbooks also write final position. They just call it X. Okay. So in some books, they're going to use this convention where the subscript 0 means starting and no subscript at all means final. Other textbooks will use subscript I and F. And I don't mean to mess with you, but sometimes I may accidentally slip back and forth between them. All right. All right. So what's A sub X? Take a guess what that means. Yeah. Is it the initial or is it the final? Do you see a subscript I or a subscript? Yeah. So what do you think? It's constant. This equation is a special one. It's only valid for constant acceleration. So A sub X is just the acceleration. It's both the initial and the final and everywhere in between in the X direction. And I suppose here, we should probably mention what's the only other symbol here? T, all right? T we would sometimes call the elapsed time, all right? Time after the starting gun was fired or whatever you want to think about. Now, you are probably like me in that you are lazy, right? You want to write down as little as possible while still passing this class and getting six-figure job, right? That's our goal here. So most people would never want to write this I hat because it immediately would drop out of the equations. We're not going to write that I hat all the time. So it's crucial that when you're doing problems, talking to others, communicating, you make it clear that when you're doing these special types of problems, the V means velocity, not speed. The X means position, not distance. Okay? Acceleration here would technically be a vector based off the definition, right? So it's the X component of the acceleration. So to be clear, most of the time, we're never going to write this. because it just takes extra time. And then in the next line of the equation, you would immediately drop it out. This reminds me a little bit of what we were talking about in chapter 3. Remember when we talked about a general vector? Or sometimes we could write it like this. The idea, oh, the screensaver's on again. Okay. Remember carefully, we talked about this last time, and I'm a stickler for this. I want you to understand this because I think it will help you communicate more clearly. Remember that this part right here is called the scalar component. Do you remember, did the scalar component include plus or minus signs, or was it always positive? Do you remember? Could the Vx in a vector be positive or negative? Yes. Right? And this was called the vector component, right? It was plus or minus with the I hat. Remember that difference? And then they both had the units. Do you notice what we're really doing over here in our equations is we're using the scalar component style of writing everything, right? We're assuming the I hat's going to be there if we had to use a vector, but we're not actually writing it. That's exactly like the scalar component. My only reason for mentioning this is you better believe that these numbers can be positive or negative. Okay. All of these can be positive or negative. Well, this one's kind of special, right? Could you have negative time? Maybe if you're a physicist doing weird stuff in grad school, but that's not us, okay? We're going to assume t is always greater than 0. There's some time reversal symmetry problems. If you want to learn about that later, I feel sorry for you. It's cool, but let's not go into it. Okay. When you go for a walk, you might walk for 10 feet, you might walk for 10 miles, right? If I say I walked for 10 miles, what do I mean when I say 10 miles? What is that position, distance, or displacement when I say I walked 10 miles? Just go with your gut. Don't overthink it. Oh, okay. I heard a lot of words. That's good. And I couldn't tell what anybody said because you all spoke up. That's awesome. To me, when I walk 10 miles, I'm walking a distance of 10 miles. Okay. Displacement is different than distance. Position is different than distance. Position is where I'm located. Distance is how far I walked. Displacement is how far I am from my initial position with a direction and a distance. And more on that in a minute, but again, position, where I'm located. Distance, how far you moved. Displacement, how far and the direction. So far, so good? You have a question?
Oh, no, I just remembered something that I heard that helps to understand this displacement. It was if you die in the same hospital that you were born with, your technical displacement is 0.
True. Yes. Well, think about this. You run laps around a track, then we don't have to die for the problem.
Okay.
I mean, I appreciate the attitude that you're willing to die for a physics problem. That's cool. But for most of us, let's say, right, if you run around a track, and let's draw a picture of this here. Well, let me do this. There's 3 keywords that are most confusing. Distance, displacement, and position. Okay, and I'm running out of room on my whiteboard. I'm going to erase this general vector over here. We don't need that anymore. sec. Marking the end, okay, making sure my camera's right. Okay. I'll get out of the way in a second. Distance is how far you traveled. Displacement is probably the best way to say it is to use the math terms. Final position minus initial position. Position is where you are located. And I'm going to add in a couple of extra words here. Relative to an origin. Okay. All right. Now, in this case, think about, I think it's much easier to understand displacement once we truly understand position. One of the key things here in this, if you want to understand somebody's position, you need to have an origin. You need to have a coordinate system, right? I don't care what it is. You could say the town hall in Toledo is the origin. You could say, you know, this brick is the origin. You have to pick some spot in the universe that you say is the origin. After that, right, let's say we say this brick over here, which no one could see on Zoom. So how about this dot right here? If that's your origin, right, I am located at some X, Y, and Z relative to this dot. So are each of you, right? If I move, I'm at a different X, Y, Z. And then it's really easy to get displacement. Just take my initial X, Y, Z and subtract it from my final X, Y, Z. So far, so good? Which of these are vectors? What's that? Okay, a displacement is a vector. So what does that tell you about position? Yes, right? Do you agree? If you have an origin, you have to tell me how much in the I hat, J hat, and K hat. I hat, J hat, and K hat immediately makes me think vector. Good. You take a difference between two vectors, you get a vector. Distance? Scalar. Nice job. All right. So why am I belaboring this? Because I've graded a whole bunch of physics tests in my life. Every time on the first test of the year, there's always people sticking in distance for X, and it pisses me off. I hate it. So you're in a hurry on test day. I can understand how you make the mistake. But please, 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 remember there's a difference between distance and position. Got it? I cannot stress that enough. And here's why students do it a lot of times. For many, 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 many problems, what's a good value for the initial position? 0. So in a great many problems, we start at the origin. Furthermore, for a lot of problems, everything moves to the right. If you have a problem where you start at the origin and the object moves only to the right, in that special case, distance and position have the same size. The magnitude of the final position is the distance. But every other problem in the universe, here's one. Let me see if I can do it. Let me zoom out a little bit. All right. Could you do me a favor and just like roll that way for a bit? The back of your head's right in the demo for the Zoomers or whatever. Yeah, thanks. Perfect. Appreciate that, man. Sorry about that. Didn't mean that. I didn't expect it. Okay. Here's a cart. Okay. Is that showing up on Zoom? All right, we're good. Now, in this case, when we're looking at this thing, would you say this cart is moving in 1 dimension, 2 dimensions, 3 dimensions? What do you think?
I'm moving to the one.
Well, let's think about this. Normally, x means to the right. Do you agree? But if instead of using this as our coordinate system, what if we just rotate it? Then it's moving along a rail. So we're going to see that sometimes even when things aren't moving right, this is something in the x direction. The reason I have to tilt it is for this. It starts down here. Let's say the initial position is 0, right? At the brick. You can see the brick now, right? This is the brick, Zoomers. All right. It goes up the hill. It does a couple of bounces and it comes back down. Its initial position was 0. What is its final position? 0. What is the displacement? What is the distance traveled? 0 or something? Something, right? We see that this is the crucial, and this is what he was talking about. If you die in the same hospital, blah, blah, blah. Okay, so in this case, what we're going to do with problems is if we can see something that's moving in a straight line back and forth, we're going to try and analyze this in 1D motion by rotating our coordinate system so that the x direction points along the path, or dropping it straight up and down would also work. All right. All right. Any questions right now? I've been babbling for a long time. Questions? All right. Yes.
So later on, I know we're going to be rotating axes and stuff for that. And it's like, how does that affect? How does that affect problems in the real world if you rotate an axis?
Yeah, this is a good question. Coordinate systems are completely mathematical constructs in our minds, right? We decide where the origin is. We decide what direction the x-axis points. Let's be fair, most of us, when we're working on paper, say x is to the right and y is up. But it's purely mathematical. If you choose a different coordinate system, the fundamental physics properties of the problem should not change. And by that, I mean, the time it takes to get somewhere should change based on how you draw a couple of lines on a piece of paper. The total amount of distance traveled shouldn't change based off whether you draw your lines this way or that way, right? And in fact, this was one of Einstein's postulates in special relativity. Physics should be independent of the coordinate system. And from that, and that the speed of light is a constant in all reference frames, he found some crazy stuff. Anyways, we'll worry about that in Physics 162. Short version is, you could draw your coordinates however you want. She could draw hers however she wants. In the end, you'd better get the same answer for the time it takes to go somewhere or the distance traveled. Is that good? Now, that said, usually it's nice if we all try to use the same ones because it makes it a lot less confusing to communicate. I could make x point up and y point to the right, but we'd have a lot of trouble communicating because we constantly say, my j hat, plus your k hat would be one way and my k hat would be the other way. Good enough? Yep. All right, good question. Coordinate systems shouldn't matter. And yet, if you don't pick a normal one, it's really hard to communicate. Anything you want to say about that, Don? Okay, got it. Yeah. Generally speaking, we want to try and write things in the standard form just so it's easier to talk. Other questions? How about you on Zoom? All good out there? And don't forget, if you're on Zoom and you maybe feel shy about talking, Jules is in the room. You can text Jules and Jules can just shout out the question for you if you want. All right. So, all right. What's that? Oh, yeah.
If I remember right from 110, if you make that your axis, doesn't that affect the sine and cosine?
So, yeah, so that's the thing, right? You could view this problem right here as a two-dimensional problem. You could say it's going some in the x and some in the y. And then you could say it has some acceleration in the x and some acceleration in the y. And those acceleration x and y and velocity x and y would probably have sines and cosines in them. What's cool is by rotating this coordinate system, then we have everything everything perpendicular to the plane would be 0. So there's no velocity in the y. However, the acceleration in the x would have that sine theta hidden in it because of the rotation. In fact, if you want,
Yeah, sine theta.
yes, take a look at page 24 really quick. Problem 2.2. Page 24, problem 2.2. You see that there? That shows you some of the different ways. Notice there's problems 2.2, 2.3, and 2.4. They're not all the same. I've shown some examples with different coordinate systems in there, and we can work through those in a few minutes. Is that cool? Yeah, yeah. So I'm trying to get us set up for that problem in a minute. All right. I'd rather make sure we get this right. So I'm not going to skip problem 2.1. Let's go to page 22, and I want you to read problem 2.1. Okay, I'm going to get the board erased. You can skim ahead and read that, and then I'm going to do the visual, and we'll do that problem together. 2.1. What page was it again? 22. I appreciate you hanging with me while we do these fundamental definitions and stuff. At this point, if you feel like you know what you're doing, you might want to race ahead, but okay. All right. I'm on the wide view, good. Okay. So just give me a second here. Take a look at this. Now, I hope this is working on Zoom. I can't remember which way, like if the image is mirrored or not. So I apologize if in the recording, when I say move to the right, I'm moving to the left. So I hope so. Is this moving to the right on your screen or not? No, it's off. It's opposite. Okay. Well, shoot. I don't know the mirror button right off the hand. I didn't think. Video settings. Mirror my video. There we go. Now let's try this again. That's to the right now? Yeah, okay. All right, so, and then I gotta remember to unmirror it or else all the text is gonna be screwed up. Okay, I think I got it. So here's the idea. And this problem, let's say this line right here is the origin. And we're just gonna talk about x direction, so we don't need to worry about z or y. I'm gonna go this way for a little while. And then I'm gonna go backwards for a while. And then I'm gonna come back to my starting position. So again, I'm gonna go forwards. I'm gonna go backwards. And then I'm gonna go forwards again. All right. So in this case, you've got a big table there. You can kind of see the pattern. I tried to draw it out here in the workbook. Let's take a second, talk to your neighbor, fill in the chart. In particular, think about which things need units or not. I believe all the units are written for you at the top of the table, so you don't need units. But what about I-hats? Some of them might need I-hats, some of them might not. Okay, fill in that table. Will I get the table written up on the board as well? And talk to your neighbors as much as you want. And then Jules, if you want to slap around, that's cool. Okay. you forget what the symbols mean, you could read page 21 to say like, wait, what did he mean by delta x? Did he mean distance, displacement? You can watch up there on page 21. There's the definitions if you need them. Notice we've got speed and we've also, I got it. I don't know who that is. Don't forget you've got the solutions too. If you finish it, talk as much as you want. Talk to your neighbor, talk to Jules, run out of the room screaming. It's got to be done. Just going to take a quick loop around and see as well. So now you need to get these, right? Remember, what, in this case, if you had to guess, what's the difference between V and V with arrows in this context? Exactly. So if you need speed, what you could do is look over here. Remember the definitions are on page 21. Okay, right? Yes. Okay. All right. Yes. Okay. Now, here's another one. Because I wrote the units of meters, that means you don't have to. It's just a it's a trick that we're going to use. So put it somewhere else. That way you just- What's that? Good. Yes, that is what I was looking for. You agree? This is the vector I have. Here we're talking about distance, so this looks pretty good. Right? Here. 5 and 6. 5 and 6. Those are the change. Okay. 5 and 6. So if you're thinking of the total 0, 6, 7, got it. Okay. Cool, right. Exactly. That's the main difference there. One's got I-hats, and one has to figure out plus and minus, one is just distance. So very good. Okay. Which part are you thinking about? Which leg? 4 and 5. All right. Yeah. Well, so just tell me, like, in your own words, how far did it travel? 15 units, right? Okay, so we know it's 15. Now, in this case, what was the change in position? Was it 15 to the right or 15 to the left?
Yeah, kind of the right.
Be careful. Start here, and you're at 4 seconds. From 4 to 5 seconds, you're going to the right or to the left. So then that is positive I or negative I. So then you look right. How far? And direction. 15.
That makes sense.
Distance travel is 15. Displacement is -15.
Okay. Then the same thing, this is speed, this is velocity. Speed's always going to be positive, velocity can be plus or minus. Cool. So give you a minute.
Yeah.
Okay. Okay, velocity, all right. So then one thing you can do is you're not wasting it. It's got numbers, so it's got see how you do on that. All right. That'll kind of, that's how all of your right head is left outside. Right? You're doing that. Yeah, okay, cool. I got you. So yeah, just find some problem and work on it. Careful. Remember, if you get done, you can work on another problem while I'm circling the room, okay? So just keep working. Okay? What is speed?
Just to velocity. Let's subtract.
Keyword you're missing. Yeah, it's different, isn't it? It's not gravity, it's not the acceleration. It's called magnitude of over acceleration.
I'm not sure. It's just asking.
Okay, so it's basically exactly what I said and nothing else.
Oh,
Okay.
Oh.
Yeah, got it. I'm trying to show you how it works. Cool. Now, because your head, if you want to, I don't know which one he's doing, but you guys are both doing the same reason. That's the part on the same page. So you would just, how are you doing? All right? Okay. Okay, your crew's gone. Doing all right? Oh, you're working ahead? Okay. No. Right? Do you know, so that's if it's accelerating. We're going to assume it's going at constant speed for each time. Do you know the distance traveled and you know the time? How do you know? You're overthinking. You could use that as well, but it would take you a long time.
Thank you.
You think you're doing all right, right? Okay.
Just checking in with you on Zoom. Any questions from the Zoom crew? Oh, I better flip my screen while I remember it. Okay. I checked in with you two up front.
Wow. How's it going here? You guys making sense of it now? How to get in the head? Yeah. Okay, cool. What do you think? Does it make any sense? No. Yeah. This would be just, so this is K. This one is K to the right. That's the only difference. See what I'm saying? So that's this part. Now, when you go from here to here, how far does it go? Went from positive to negative 5. How far is it? Then 5 total. Yeah, and then the distance is 15. Now tell me, is that 15 to the right or 15 to the left? Yeah, so it should be. Yeah, that's all it was. You're overtaking. Got it? And then the units are up top. Got it? No. Well, you could use that if you want to. I'm just trying to get a feel for this. Yeah. Okay. All right, so far so good?
So in about 1 minute, I'm going to start working through it on the board. All right. So
Didn't it? All right, I'm gonna tell you, you got some mistakes.
And that's -100.
In this case, just between 5 and 6 seconds, we travel 5 meters. Now,
Don't add
when I write the units up top, I'm proud of you to write the units, so it turns out by writing them up top, that means what? Everything underneath that goes. Just so you know, the same time. That's how we do it. In Excel, right? If you want to have Microsoft Excel or some computer program do the math for you, you can't have the units on the number because it needs to just the numbers per stack. So what we do is we always write the units in a different place. Anyway, whatever. I did get this. In here. Between 5 and 6.
I get it.
They keep pointing to the right. Between 5 and 6, how far did you travel? 5 and 6 seconds. How far did you travel? Right. What direction? These numbers are always going to be these ones get different. These are the ones where you have to think a lot. But here, that's the distance. Here is the distance. Like direction. Plus or minus 5. Cool. Same with these numbers and these ones. Got it?
All right. You're welcome to keep working. You can do whatever you want. I'm going to start writing this up on the board. All right, so let's take a look. Between 0 and 4 seconds, how far did I travel? In the problem.
10 meters.
10 meters. Now, you could put the meters right here, but remember, because I put this in a column heading, I don't have to do that. So it's going to be, the units are right up there. Now, we're getting lazy with sig figs, so I don't really care about that. Between 4 and 5 seconds, how much distance did I travel? 15 meters. Again, 15 here, meters up top. Somewhere in the word problem, I said that it was in meters, I think. Between 5 and 6 seconds, how far did I travel? 5. So now the main difference here, as written, we're assuming, and every time, if you're not sure, you could ask on test aid, this is distance. I'm going to underline that T. Delta X in this context means what?
Displacement.
Displacement. So let's get some other color. How about purple? So this is displacement. Displacement is a vector. We need both a magnitude and a direction. The units are taken care of us. So for the first one, it's 10. What direction? To the right, or positive I hat. Now, most of you would not write it this way. Most of you would just write positive 10 I hat. And since we don't really need the plus, most of you probably just wrote 10 I hat. That's full credit right there. From 4 to 5 seconds, I know the distance is 15. What's the direction between negative I hat? So if I was going to write that, I would probably write negative 15 I hat. Again, the units are up top. And this one? Yes, exactly. Now, let's figure out the distance traveled in the entire trip. How far did this person travel?
20? No, 30.
30 meters, right? The units are up top. What is the displacement?
0.
0. This is the case where if you start somewhere, move a direction, move around, do the hokey pokey, come back to your same position. I don't care what you do. If your initial and final are the same, the displacement is 0. Strictly speaking, I should say 0 in the I hat, but since 0 times I hat is 0, you could probably leave off the I hat on this particular one. So far, so good? What does this symbol mean? If you had to guess in this context, in this problem, we see a V without an arrow on it and a V with an arrow on it. When you, these are probably speed and velocity. All right, how do we get speed? What's the equation on page 21? How do you get speed in these cases? To be clear, in this problem, it specifically said something about it's moving. We're going to assume this is constant speed, and maybe I should have said that at the very beginning, but I imply there's no acceleration, so maybe I'll put a comment on here. Some of you were saying, oh, should I use the 1/2 AT squared equation? It's a good idea, but do you see anything in this problem that talks about acceleration in the problem statement? You see the words acceleration anywhere? No. So this is kind of a special starter problem. I apologize if I didn't make that clear. So because this is an assumption we are making, I'm going to list this. This is what you do as an engineer. If you make an assumption, you make sure you tell everybody else what you assumed so they know how you did your work. In this problem, and I believe it did say to ignore the turnaround time, didn't it, or not? I don't know. Let's say that just in case. So in case that wasn't clear, I want to be clear that's what I'm assuming here. All right. If that is the case, if we don't have any acceleration, then we could use distance equals rate times time, right? So what is the speed? Distance over time. What is the distance traveled? 10, right? And then what is the time? 4 seconds. So what is our speed for the first one? 2.5, 10 over 4. That's good. All right, so far so good? And the units are up top. How about for the next one? And the last one, just 5? Is that right? Yeah, okay. Now in this case, velocity, what's the difference between speed and velocity? There's a vector. So what do you think I have to do for this one? What over time? Displacement with a P. So I want to emphasize, a lot of times you'll see me write DIST just to make it clear whether I mean distance or displacement. That's a P there. Kind of looks like a weird symbol. Whatever. All right, so what's that one going to be in the first case?
5 over 2.
2.5 I have. So the velocity has to have a direction on it. All right, in this one,
It's negative 59 I have. And 5 I have.
so now we get to the two interesting ones that students sometimes screw up badly. Okay, if I want to get the average speed, if I want the average speed, do I average the speeds?
No.
No, and that's what's confusing. Okay, the average speed is total distance over total time. Okay, total distance over total time in this case is what, 5? So what would be the average displacement? Or sorry, average velocity. I misspoke. What would be the equation for it?
Displacement over total time.
Total displacement over total time. So even though you're moving around a lot, your average velocity is 0, but your average speed is not. Now I know I spent time on this. And it's probably like, oh, this is too easy for me, or oh, I get this, or oh yeah, this is boring. There's something fundamental I want you to take out of this. It's this. Whenever something reverses direction, if you want to understand the problem, you can split it into stages. See that? In general, anytime something's motion is changing significantly, you could split it into chunks. And this is actually something we're going to do in coding all the time. If you choose a really tiny time interval, we can actually use these same types of problems. You could say, okay, it's not going to accelerate much over this time interval. We could use this equation here or whatever. So we actually use these basic equations in complicated computer codes to analyze the motion. So that's the other reason I want to give you a heads up. We're going to use this all the time in coding. I think it's a good time to take a break, don't you? It's been a long, boring start to the class. We'll pick it up from here. So let's take a 10-minute break. Those of you on Zoom, if you want to go get your coffee or whatever, get on it. All right, I'm going to take a break too. So 10 minutes, my clock says 12:09 here or whatever it says there, 12:09.
V2, and V3, and you're given the total time interval,
Yeah.
but nothing else. Is that?
Then it's gonna be tricky
Okay.
because we don't know each subsection.
Right.
But you could have a video. I could provide you a video. And from that video, you can figure out the times. Agreed?
Agreed.
So if you had drone footage of the motion and calibrated that to the size of the earth, you could do that. That's what we'll do in lab on Thursday. Without the drone and just use your iPhone. All right. All right. Well, so here we go. I'm going to do something really quick here. Whoops. Almost there. There we go. There we go. All right. At the bottom of page 22, there's a strategy for solving physics problems. It doesn't work all the time, but it's a great strategy to have. And I'm just going to write that up here. Notice the first thing. Oh, whoops. The first thing is actually read, then draw, right? Label. Sometimes I don't write this here, but I just mentioned this. If you're an engineer, you better list your assumptions too. One of these steps is more important than the others. We do it twice. Read, right? When you got to read a problem, what happens is you'll read a problem and get ahead of yourselves and then think, oh, what do I have to do again? At some point, you're going to have to reread it, right? The big difference between Physics 161 and Physics 110, or high school physics, is this step. You might be used to it, you think, but just make sure. I'm going to show you how to do this. We're going to try and solve equations algebraically before we plug in the numbers. And it's not always possible. Sometimes it's not the best strategy, but in a huge amount of cases, this is a very, very, very wise move. Okay, on rare occasions, even I plug in numbers sometimes, but almost always it's best to solve problems algebraically, then sub in values. And here's the other thing I want to have driven into your brain. You read, you draw some pictures. Don't draw tiny little pictures. Draw them a quarter page or a half page in size. The bigger you draw, the easier it is to label. Then you want to identify what's known and unknown in the problem and list your assumptions. That's kind of all one big bullet there. List your equations. If you have some useful equations that you know, reread. Remember, what are you looking for? What are you trying to find? What to find? Remember that. I'm sure that's what you're thinking. Solve algebraically. Hopefully I spelled that right, but I don't care anymore. Then sub in values and check your result. Now, some students, basically all of them on test day, will get to the very end and you're in such a rush on test day, you forget to check your results. And students will write down the most insane looking crap that makes no sense whatsoever if they just do a unit check. Or maybe they don't think about the reality of the problem. Like I had one student tell me it takes $2.45 billion to pay for the gasoline to cross the United States. I'm like, really? I had several say it was in the millions. I know there's inflation, but it's not that bad yet. All right, so anyways, checking your result is also useful. And if you don't check it when you do your homework, you're not going to check it on test day, and then you're not going to do well on the test because you missed some stupid points because you missed one minus sign or flipped something and forgot to check it. When you're doing your homework, get in the habit of checking your results. All right. Now, most of you probably have heard some version of this before, right? Maybe at some point, but let me say it like this. if you are really rusty on this, the problems on page 23 all have numbers, and you could do those problems numerically if you wanted to. Our goal is to learn how to do this kind of the more physics appropriate way of doing things, everything algebraically. So we're going to start on page 24. If you are really bad today, go back and do page 23 if you are terrible at this, okay? All right. Again, everybody comes from a different high school or different physics 110 class, so I'm not offended if you're bad at it, right? That's fine. But just know we want to get to this next level. So, all right. I'm going to keep that over here. Let's get back there. Come on. There we go. So let's look at 2.2. I'm going to draw it up on the board. You can start reading it. You can start doing it. That's some kind of a ramp. Draw your picture kind of big. If you're still doing problems in the workbook itself, make sure you stop that right about now and start doing them on paper. I'm reading the question. There's a frictionless ramp. I'm going to write down that word frictionless just because that might help me remember. If there's something important in the problem statement that you don't want to have to remember all the time, write it down. The box is released from rest. That's an assumption or a known or however you want to say that. Somewhere in this problem, it says the box has negligible size. That's kind of useful because that means I don't have to worry about, oh, am I talking about the front side of the box or the back side of the box or the middle of the box? When it says it has negligible size, that means we can kind of ignore the size of the box relative to this huge ramp. We're not going to get a perfect answer, but it'll be pretty darn close. That's what this is saying. Don't need to worry about, are we talking about the leading edge of the box or the trailing edge of the box? Okay. Okay, I read this line. It says, the magnitude of the acceleration due to gravity is g equals 9.8 meters per second squared. Somewhere it says that in there. To be clear, as a physics instructor, one of my pet peeves, g is not gravity. G is not the acceleration due to gravity. What is g? It's the magnitude of the acceleration due to gravity. Okay, to be clear, the acceleration due to gravity is a vector. Its magnitude is g. What direction does gravity pull on you right now, if you had to guess, for a standard physics? Downwards. What do we usually call downwards in terms of a hat vector? Negative j hat. So to be clear, g is the number. G does not include the negative sign. Got it? It's pretty annoying, actually, but this is very common. We talk about the charge magnitude on an electron is 1.602. We don't say the charge magnitude is negative 1.602. We use this style of describing physics constants regularly. So you always have to think, when a physics constant is defined, or read the definition carefully. Here it's a magnitude. That means it's a scalar, right? This is defined as a scalar. Not even a scalar component. Okay, it's a magnitude of a vector. It's just a number and it's positive. Okay, whatever. Okay, so we are told we got this ramp here. There's some angle theta. and we're told that it's going to accelerate down the ramp, right? And we're told that A equals G sine theta. Look carefully. The way this is written, is this letter A the acceleration, or is it the magnitude of the acceleration? Magnitude. What is the direction of it? That way. Got it? So with these physics problems, especially in chapter 2, it's super frustrating. You're trying to learn, you're trying to do a good job, and your teachers and your textbooks will always keep kind of glossing over when is it a vector and when is it not. I'm trying to make that explicit just to help you out. I apologize if I'm boring the crap out of you. All right. Now, this looks like it has both an X and a Y component here, right? So what I want to do is I want to erase this line of text and then change my coordinate system. The reason I want to erase this line of text is if I rotate my coordinate system, do you agree that would no longer be true? If I rotate my coordinate system, J hat would no longer be straight down. So I probably should have said G downwards. How about I say this? Now, this is still a correct statement, and I can also rotate my coordinate system. We're going to derive this result later. But just so you know, that's going to be my coordinate system. I got a little block here. So far, so good, everybody? I'm going slow just because it's our first one. Oops. It says the length of the ramp is L. I still haven't gotten that in my figure yet, so I'm going to try and get that in here somehow. Now you can tell the length of the ramp is supposed to be L. All right. I argue we have read the question and drawn it. My picture's big. It's got some labels on it. What was the next step there? Identify what's known and unknown. Now, in this case, I like to make a chart. And I'm going to make that chart right here. We can do this in a lot of different ways, but I want you to get used to this habit. And before we get ahead of ourselves, you might be saying, well, what does he mean by delta X here? I want to be clear here. On all of these, there is an implied I hat. So all of these are going to be vectors. Remember at the beginning, I said we don't want to keep writing that I hat all the time. For this first problem, I'm going to include it here. Does a sub x need an I hat or not? Is it a vector or not? Yes. How about time?
No.
No. Okay, so that's why time doesn't get it, right? Time is the different one. It's a scale. So in general, when you're reading the solutions, you're not going to see this, right? But you're supposed to know it's there. Everybody okay with that? All right. Tell me what this means then. What does this symbol mean? Before I waste time trying to figure it out, what does it mean? Is it position? Is it velocity? What is delta x with an I hat on it? Displacement. Excellent. To be clear, that's the same thing as x final minus x initial in the I hat. Do you agree?
Yes.
Okay, so this is just a different way of writing it down. Some of you, if you're used to doing this a different way, some of you might have written x final and x initial. Remind me, what does x final mean? X is distance? What is it? Acceleration? Yeah. Does it need an I hat or not? Is there an implied I hat? I should say it that way.
Yes.
Yes, yes. So to be clear, some of you might use these two blocks instead of this one, and this would be final position. And this would be initial position. There are pros and cons to each method. Now, in this case, let's go through and fill these out. What is the displacement in the I-hat? Oh, go ahead. What's that? L. Is it positive L or negative L? Is it L going with the x-axis that I chose, or is it L going against it? With it. So it would be a positive L. Is everybody okay with that? Now, you're not going to write the plus sign. I'm just trying to emphasize that it's going with the coordinate system. Plus, because going with coords. Everybody okay with that? How about V initial X? What does that symbol mean again? Okay, initial velocity. What's the initial velocity?
0.
How do you know?
Sorry.
Okay, got it. Because init at rest. Sweet. I love zeros. What's V final in the X? We don't know it? Okay, how about I just put a question mark right now? Do I know what a sub x is? G sine theta. Now, I don't know if we know what theta is, but do you agree we know it's G sine theta based off the way they wrote this in the problem? I guess I wrote it, but whatever. Wait, is it plus or negative? How do you know? Plus, because with positive x direction. In some other problem, it might be negative. All right, all right. Time, do we know the time? I don't know if we know the time or not. We gotta read this damn problem again. Ha! Nice, Dom. Well, that means everybody gets an A. Okay.
I think
Wouldn't
we're
that be-
solving for the angle to find time.
Okay, we're looking, okay. Okay, so eventually this time is gonna be T. If you read part A, the time, so this is one of the things that probably is frustrating for students that are first getting used to solving problems algebraically. When you read the problem, if they tell you a variable in the problem, like in this case, they said, how much time to reach the bottom in time t? If it takes time t, they're implying that t is a variable that you know. Similarly, they said the length is L. So we're supposed to assume L is a variable we're going to know. All right. G was a variable we were told. So, okay. All right. Now, in this case, here's the thing about the final position and the initial position. We could choose where to put our coordinate system. Usually, we set x initial equal to 0. So this coordinate system would have the origin right there. If we do that, the initial position becomes 0. What is the final position?
L.
L, positive or negative? Positive L. Got it? So far, so good? All right. Now, I think we've got most of our equations, most of our assumptions listed. The next step is to list our equations, right? Now, what do I mean by that? Tell me any equations you can think of that might relate to this problem. Give me one, any equation, and you can read the back of your workbook if you want. Kinematics equation? Somebody said kinematics, I like that. Give me a kinematics equation.
Would it be V final x equals V initial x plus AX times T?
I like that one. Now, you'll notice what I did here is I left a little bit of space. If you're writing down in your notes, I want you to leave a little bit of space in here, maybe like 4 or 5 lines between each equation. And this one was going to be the second one. A lot of you probably know this equation. which is the one we started class with. If it helps, this was the one that said x final. I forget which way I wrote it on the equation sheet. It's the same equation. I just want to show you that, look, if you bring this x initial to the other side, you get delta x. Again, if you bring this x initial to the other side, you have x final minus x initial, you would have this delta x equation. All right. And then this last one. The reason I like this one is it's just one less variable to write. So that's why oftentimes we use the delta x equation. But you can totally use this initial and final. It works great. It's awesome. I think that's actually how I learned it when I was in college, and then I just got out of that habit and got into this stuff. These I call the big three kinematics equations. Now you wrote them. Is it legal to use them? Just because we can write them doesn't mean they apply. They do apply in this case, but how do I know that these equations actually apply?
Oh, when acceleration is constant.
Yes, these are constant acceleration. Is our problem constant acceleration? Let's go back and look at it for a sec. Over here, is G a constant? Yeah, is the angle a constant? Do you think I'm changing the angle of the ramp while it moves down the ramp? No. Is that something that could be done? Sure, but that would be a much harder problem. We're not going to do that one. We're assuming the ramp is just sitting there and the box is sliding down. So far, so good? All right, all right. So that's why it is okay to use these equations right here, because it's constant acceleration, and ours was A equals G sine theta, and we're using a fixed theta. It's okay for us in this problem to use these. Now, just so I have this here, give me a sec. I've got my equations, I've got my symbols here. That's our list of knowns and unknowns. The first step that I like to do is plug in anything equal to 0 and simplify the work. Okay, let's get our zeros in there first. So anywhere we see a 0, let's drop that in to make life easier. And now, again, I'm going to kind of ignore these two down here just because I wrote my equations in delta x form. You could do it this way, but we don't need them. So basically, anywhere I see a v initial x, I can plug in a 0. Let's do that first. That's a much easier looking equation to deal with. Before I do any algebraic work, plug in anything that's equal to 0 to save yourself some messy algebra, right? Down here. So for this particular problem, that's a huge benefit, right? I'll get out of the way in just a second. By plugging in the zeros, our equation gets dramatically simpler in a hurry. All right. Now let's go ahead and plug in all the rest of these other variables. Maybe you said, why didn't you just do that in one step? That's fine. I just wanted to emphasize how important it is to get the zeros in there right away before you do algebra. Okay. So now this equation is going to become, what was a sub x? G sine theta. Okay. Oh, wait, what was delta x? L. Now we have an equation in terms of the variables that the problem told us. And that's the main difference between having numbers to shove in and having alphabet soup to plug in. All right. In this case, I guess we're going to get there's another equation. And then in this last one, I guess we're going to get Here I moved the L over just so it's sitting out in front of the sine theta. I probably should have done that right here too, so I'm gonna do that right now. Usually we leave the sine theta sitting there at the end. So again, I just rearranged it a little bit. Is everybody okay with that? Some of you might be saying, aren't there more equations? Isn't there a fourth one or a fifth one? Yeah, but whatever. If you could, I've been doing physics with just these three equations for about 20 years and it seems to be working. So I know it'll work for you too. Are there sometimes a shortcut with a fourth equation? Yes. If you want to use that equation and you memorize it, I'm cool with that too. Okay, whatever. What was the point? What are we trying to do? This is when we're supposed to reread the problem and remember, what are we looking for? I have no clue. What are we doing? Determine angle required to reach the bottom of the ramp at time t. Answer in terms of L, G, and T. So in this case, what symbol are we trying to solve for? Theta, in terms of which variables? L, G, and T. What is going on here? Come on, monitor. All right. Which of these equations is going to get the job done most easily? The first one, right? This one, I don't know what VFX is. I could probably figure it out later, but I don't have it right now. So let's do this. We're trying to solve for the angle, right? So get it, go. I'll race you. Solve for it algebraically. Try to screw this up. Divide by 2, divide by GT squared on both sides, I think. That should get rid of the G, T squared, 2, yep. What operation do I do to get rid of the sine?
Arc sine?
Yeah, arc sine, sometimes we call it sine inverse, yep. We're done, right? What do we do when we're finished getting a result?
Plug in numbers.
Okay, true. What else? Yeah, we could do some checks and plug in numbers at this point. So I think in part B, didn't I give you some numbers? Yeah, in part B, I gave you some numbers, I believe, or something. I don't know what. But let's do the unit checks before we go on. So at some point in this process, let's check the units. All right, people.
Mr. Jorston,
Go.
can
Oh.
you pan the camera to the left a bit?
Sorry about that. Thanks for saying something. Is that better?
Yes, thank you.
Thanks, boss. Okay, check the units. Tell me, what's up with this? What are the units of theta? Radians or no units? Right?
Degrees are considered.
No, we would not want to use degrees in general for a unit check. That's a good question. This is a function. What are the units of the entire function? Do you remember that from chapter 1 in the homework? This is unitless. Now, some of you may not remember that because you maybe didn't get to that question yet, but that's unitless. That's good. So the dimensions of functions are unitless. So does this match? We could do it even better. This is the argument of the function. What are the units for the argument of a function? When you punch in something into your calculator and you want to do e to the x, do you have units on that number when you type it in your calculator? How about units when you type in sine or cosine? How about inverse? So take a guess. It should have what kind of units? No units. This is also dimensionless. Okay, so what are the units of 2? None. How about L? Meters. What are the units of G? Now, when you're doing this, heads up, everybody, listen. Try to use horizontal fraction bars only, okay? Because if you start using diagonal fraction bars for your unit checks, it just turns into a mess, and then you start, just trust me on this. Use horizontal fractions almost exclusively until you're really, really good. T squared, what are the units of that? All right, so when we do this, second squareds drop. I got meters over meters. No units is no units. Feeling good on that? All right, all right. So far, so good on this? How many of you, and I'm not offended at all if you don't do problems this way, or if you had it in high school or whatever, but have some of you done this before? If you have, thumbs up. If you haven't, thumbs down or sideways, just kind of, okay. So was that kind of a good review, even though it was slow? All right. Are you okay with me doing some slow problems at first, even though I just don't want to punish you guys, right? I don't know what you all know. It just seemed like last time when I skipped a problem, you guys were just trashed. So I'm going to do a slow one first every time, okay? Just to kind of catch you up. And so I apologize if I'm ever boring you. If I'm ever boring you, do the homework and work without me, okay? All right. I'm going to read the question. I have no idea what we're trying to do right now. Okay, that was part A. Do you agree we finished part A? So maybe what I'll do, all right, part A, the answer was theta . Some of you might have this question. What if my calculator was in degrees mode or whatever, right? Well, that's fine, right? So if you want to get the angle in degrees, at this point, when we're doing the unit checks, we think of the units as being radians. But if you're punching in numbers, hell yeah, use degrees. You know what I'm saying? If you're doing the problem on a test question, you want to get the answer in degrees, use your calculator in degree mode. It's just for the unit checks. I want you to think of theta in radians. Everybody cool with that? All right. Part B. I bet you could get there before me. I think it's a totally different question. Take a second to look at it. In particular, think about this list of crap that you know. How is it going to change? How is it going to be different, etc.? Okay. I'm going to erase the board and get caught up. If you want to finish it, go for it. Okay. And you can finish the rest of this problem. And if you finish it, you could go on to one of the other problems. All right. Talk to your neighbor as much as you want. It's going to take me a bit. So, Jules, if you want to circle around, you can and just kind of help out. Students, be proactive about speaking with Jules. If she's coming around and you don't understand something, make sure you talk to her, right? She's pretty darn clever. We want to use that resource. Dom, on the other hand, just ignore him completely. Those of you on Zoom, I'm just erasing. Trying to get there. I think I'm ready to talk about part B now. Let's see. I'll give you a second. Let's go around the room once. I'll give you a second to look at it and we'll see if we could find any mistakes. Or if you have any clarification questions, so on Zoom, oh, let's see. It's kind of fun, Kiana. The only thing I would say is, Kiana, I would modify that. I would make it that, because you want to solve it algebraically. So I would not substitute. That's a bad strategy as written, but you probably knew that. So definitely you want to do everything algebraically, especially because more than half of the test questions will not have any numbers. So it's impossible to solve them without doing the algebra. I'm assuming you're good with that, right, Kiana? Okay, I'm going to keep circling the rooms.
Calculator is the appropriate angle measurement.
The calculator?
No, that's your angle of gravity.
How you gonna do inverse trig problem? Catch. Do the back in the hand, right? You want to? You got one in your bag or not? So start bringing that scientific calculator every day, just so you can start getting used to using it. That way you're fast on test day, right? You want, in order to do well on tests, you need to practice everything like it's a test. Use the same tools, right? You can use the equation sheet on the back, so that'll simulate a test equation sheet. All right. I'm going to go ahead and start doing part B on the board. If you want to listen to me, that's cool. If you don't, whatever. Oh, I think it was. Wait, this, oh, we had all the information. I just erased it. Damn it. I can rewrite it real quick. He said theta was equal to the sine inverse of, what was it, 2L over GT squared, right? So in this case, it's sine inverse of 2 times 2.00 meters. D was 9.8 meters per second squared. Even though it's only got 2 sig figs, it's very close to having 3 sig figs. What was the time? Did we know the time? 1.40. Notice the units will still work out. What did you get for theta? Anybody? All right. Now this is cool. We'll worry about the sig figs later, but it's about 12 degrees. Do you agree? All right. Let me see here. Turn those on. I'm getting this thing to 12 degrees. Let me get my demo on the screen here. Okay, and let me do this. All right, so here's our demo, right? This is 2 meters long. All right, is the size of this cart negligible? What do you think? Just tell me your gut. Kinda-ish maybe, but not quite, right? But to a first approximation, we're going to assume this is tiny. It'll be in the right order of magnitude. It'll be approximately right. Okay, so when I raise this thing up 2 meters, it's actually only going up maybe 1.9 or something. So we might have a little bit of error there, about 5%. 1.9 out of, right, that's 0.9. And then what's our angle got to be? 12? You just told me it needs to be 12 degrees. I'm looking at this angle indicator right here. Pretty close to 12. I'm within a half a degree. There's going to be some error in that, right? Okay, you got your timers? We're going to say 1, 2, 3, go, right? So you stop it when you see it hit the brick. Start your timer. Practice your timer real quick. Make sure you know how to start and stop it and reset it. Got it? Good? Okay, on your mark, get set, go. All right, give me some times. What'd you get? 1.2.
1.32.
Somebody else.
1.22.
What else?
1.06.
Okay, what else? Who's next? Did you get one?
Yeah, that's my.
Oh, that's you?
1.27.
1.27. All right, when you average these, looks like about 1.2. It's not exact, is it? There's an error. So usually we will address this in lab, but the idea is you could see there was a number of factors here. One was I could be off a little bit on the angle. How does that error in the angle propagate through? Oh, we'll discuss that in lab. What about the reaction time? Does anybody happen to know a typical human reaction time? About? Somebody's been smoking a lot of weed. No. 3 seconds is long. That's like every edible in the store. So 0.2 is about right. So yeah. So maybe you were thinking of 0.3 seconds.
No,
Right.
I still got one guess.
Oh, okay. Do you agree that 3 seconds is like less time than the entire? So you can see right here, clearly it's, yeah. So it's just fun to talk about weed, I guess, but whatever. In this case, imagine if everybody in the room had trouble synchronizing with me because we didn't practice in advance. We just did this once and let it hit, right? You could easily see everybody being off by about 0.2 seconds. In fact, there's 2 systematic errors here. One, this cart didn't actually go 2 full meters. It went a little bit less. What should that tend to do to the time? Shift it up or down? Down. Then there's reaction time. You probably had trouble syncing with me on go, and you might not be using these timers. So the systematic errors in the experiment are, we didn't quite have the full 2 meters, and it's hard to synchronize the times. So this seems totally reasonable that we didn't get 1.4 like we predicted. So far, so good. How could we do better? We could get a slightly longer ramp so it moves the full 2 meters. We could use an electronic timer so there's less reaction time issues, things like that. That's what physics is all about, doing incrementally better. You do this quick, dirty experiment, we get an idea, see if it works, then you get better and better. So far, so good? All right.
You could code it, then it'd be perfect.
What's that?
You could code it, then it'd be perfect.
You'd think that, but even codes are not perfect, right? So codes, now this problem, you maybe could make perfect simulation of it in a code. But in the real world, there's also air resistance, and could you account for that exactly? And then we could get better with that in our code. But it turns out in the real world, accelerations are never really exactly constant. Think about it. When you put your window outside of the car and start driving. What am I? I'm in England. Hello. What England, Bolt? Anyways, yeah, there we go. Yeah, anyways, so if you're driving, when you first start driving the car, you don't feel much air resistance. As you pick it up, you're going to feel more and more air resistance. There's different amounts of force. The acceleration could change. The cool thing about coding, though, is we can get arbitrarily close and we can arbitrarily reduce our errors if we have enough memory. So you're never going to be perfect, though. And in those situations, what you do is you split the problem up into 1/10 of a second or 100th of a second, so that over each 100th of a second, the acceleration is approximately constant for that one stage. Then you do these, you basically use that A equals dv dt and V equals dx dt over and over and over in tiny little dt's, and you're doing calculus with the computer. Anyway, so yeah, something like that. And that's what we'll do in class as well. Good? Yes.
So do you sort of like take it to like a minute?
What's that?
Do you sort of take like the time to like?
Well,
like infinity?
a short version, like in the code. Is that what you're asking
Yeah,
about?
like when you're just dividing it by like one or 6.
Okay, so the easy way to do it is just keep reducing the time step until the answer stops changing to however many sig figs you want. So if you want 3 sig figs, you start out with a dt of 1. Then you make a dt a little bit smaller, 0.1, and you just keep shrinking that dt until your answer doesn't change in the third sig fig anymore. So you don't even have to go that far. The other thing you could do is understand limits and all that work too, but we can discuss that more in lab. Is that good?
Yeah.
Yeah. So far, so good? Okay, let's look at two other problems because we still got a couple of minutes. Look at problem 2.3. Don't do it. Look at it and read it, and then I'm going to ask you a question. Talk with your neighbor if you want. If you want to, you could try and write out the chart for problem 2.3. Actually, that's what we're going to do together. For 2.3, we're just going to write out this chart. We're not going to do all the algebra every time. We don't have the time. So talk to your neighbor, write out your chart, then talk to your neighbor and see if they have exactly the same as you, and if not, discuss. Okay, try and get this chart of knowns and unknowns. If you can get that chart, usually you could do algebra, right? If you can't get that chart, usually you fail. So it's crucial that you get that chart right. I'm going to draw this. Ooh, I just turned some things around a little bit on this one. Ooh, spicy Jorsted. Okay. So give me your attention for a second, just so we can get through this. I want to say one thing here about coordinate systems and how I draw them, just to make sure you understand the way I talk. I'll give you a second to write down whatever. I'll give you 30 more seconds. It's cool. A lot of people are writing. I'll wait. All right. So maybe you're in the thick of it. Just try to give me your attention real quick because we only got 10 minutes. I want to get us out of here on time. All right. Take a look at this one. I always draw my coordinate systems kind of off like this. Now, to be clear, I just do that so it's easier to see things in the problem. Really what I mean is there's a coordinate system right here and here. Is everybody okay what I mean by that? I'll draw it over here just so it's not cluttering up my figure, but really it's at the center of the box or whatever. Okay, what is delta x for this problem? Somebody, what's delta x in problem 2.3? 3/4 L. Just because the ramp is L doesn't mean it goes up the whole distance. So if the entire ramp is L, this particular problem says we only go up about 3/4 of the way. Plus or minus? How do you know? According to what? We called that the positive direction. Okay. What's the initial x? Okay, did I use a symbol for it? V0. V0 was the symbol I used. So V0, and I'm going to clarify that's unknown. The words in the problem say V0 is an unknown in this case. Okay, what are we trying to figure out here? Where is it going? Okay, the block side stick up before it comes to rest. Okay, so what's V final x? 0. What's the key word?
Rest.
Yep, comes to rest at 3/4 L. So that's somewhere in the words of the problem. Nice job. What's a sub x? What is it?
G sine theta.
No,
Negative G sine.
negative. Do you agree that you had the right magnitude, but because, so that's where I was trying to be a jerk. Because I changed the coordinate system on you, we know the acceleration is down the ramp, but I called up the ramp positive. So watch out for that. I'm not trying to be a jerk. It's just when I write these problems, it comes naturally. I wish it wasn't so easy, but yeah. No, just every different problem. Like for me, I don't know why, when I drew this problem, it just seemed like up the ramp was a good way to call positive in this problem because it started here and it's going that way. When we do that, it makes sense to call A negative G sine theta. So notice this A, just to be clear, A, the magnitude of the acceleration. And then here, because directed opposite the coordinates, right? Because our acceleration arrow in our picture is directed opposite the direction of our coordinate system, that's where that minus sign is. Everybody cool on this one step? It's the most common mistake. That's why I'm belaboring that so much. If you get used to this, always checking your arrows versus the coordinate system, you're good. Don't think of plus minus being up, down, right, left. Think of it as relative to the coordinate system you drew in the picture. That's what matters. T, do we know what T is? I don't know. Who cares? Do we know it in this problem? I don't think we do. Do you agree? If you're doing these problems right, usually there's two things you don't know and two things you do know. So that's kind of a check on these problems. If you write it in the delta X, all right, formation. Now, from here, you could write down some equations, plug in what's zero, figure out some stuff. Agreed? Let's move on. It's most important to me to focus on the setups here because I'm confident you can do algebra. I've written the solutions. Let's go to problem 2.4. Look at 2.4. Take a second to read it. I'm going to switch boards here. We're looking at 2.4. Discuss it with your neighbor after you read it. See if you can get the same chart written for 2.4. We're slowly picking up the speed here. D number of problems dt is a positive number. Bad joke. That's a nice marker. Those pictures big. Okay. Okay, block is kicked. After the kick, it moves with this speed. Got it. The acceleration is g sine theta directed down the ramp. I guess we know g is 9.8, right? Some of you are like, shouldn't it be 9.81 or should it be 9.806 or should it be 9.79? It depends where you live on the world. Who cares? It's approximately 9.8 for this section of the class. Some of you might say, I used 10 when I was in high school. That's a pretty good approximation too, but I'm just going to use 9.8 because I'm lazy and this is approximately 3/6. So just so you know, if you use 9.81 and we were off and I counted you down on a test and you point that out to me, I'd be like, oh, whoops, all right, whatever. Okay. But don't use 10. Use either 9.8 or 9.81, whatever you grew up with. Okay, now it's time to go, but let's try and get this at least hashed out here. Most of you would probably write the set of equations. And I apologize if I'm going over a couple of minutes here. If you've got to get to another class, I'm not offended at all if you got to leave. But I'm going to write it out because we're so close, okay? We know there's an implied I hat on all this junk except for the t, right? So we don't have to keep saying that. In this problem, what's the acceleration I should use? Is it positive g sine theta or negative? Negative, okay. Why? Explain why really quick. Nope.
Well, it's going opposite.
Going opposite the coordinate. Now, in this case, downward was opposite, but I want you to get in that habit of saying it that way. Cos opposite direction of coordinates. Got it. Do we know v final x? I think that's what we're looking for. We know the time in this problem, right? What's v initial x? That was, is it 3.834 or is it negative 3.834? Positive. Why?
Is in the direction of the coordinate.
Yes, yes. In the same direction as the coordinates. All right. Let's not get in the habit of using those diagonal fraction bars. Delta x, do we know it? No. Is this going to be a number? Do I know this number in theory? Do I have the angle in G? Yeah, so in theory, we know this is some number, right? Two unknowns. This is what we expect. So how would you get the speed after 1 second? Just remind me, how would you get the speed? Any ideas for equations you might use?
Second conversion.
Yeah. Do you agree? Check this trick out. I'm going to write down an equation. See, do I know the time? Yes. Do I know a sub x in theory? Do I know v initial x? So I can get this. So am I going to get the speed when I plug in the numbers? No. Why not? I know what happens in this problem. You don't. When you plug in these numbers, 1 second, it's on the way back down. Gotcha. It reverses direction, doesn't it not? Blah, 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 or a bunch of words. You don't know when this thing reverses direction, do you? I do. It's less than 1 second. If you solve this, you're going to get, punch it in. Hurry, hurry, hurry. Just give it to me, quick. Or if you have it on your phone, tell me the number. Right, the initial is 3.834 minus 9.8 sine 30 times 1. I got negative 1066. Do you agree that's not a speed? You see what I'm saying? Gotcha. Don't you hate physics? Every question. What does v final x mean? Remind me. Nope.
Final velocity.
This is final velocity. You still have to think about there's a hidden I hat in there. Oh no. Ah. Speed is the magnitude of that. if I want to get the distance traveled, what equation might I use? I know we're almost done. I appreciate the extra time. I hate doing this to you, but I'd rather have it on the video all in one spot. What equation do you think you would use for the distance traveled? What's the kinematics equation that kind of jumps out at you for distance? Yeah, delta x. But we're going to run into trouble when we use this equation because it turns around. So this is not going to give you the distance. What does delta x mean physically again? Displacement. So displacement is not distance. So what you need to do is, the steps would be 1, determine time to reverse direction. Is that still showing up on Zoom? Is it on the board? It is. Let me get in just a little bit closer. Sorry. I'm just slower at the Zoom. I can't help it. Oh my gosh, whatever. All right. Then get delta x1 for the way up, delta x2 for the way down. Do you know what I mean? If you know delta x for the first stage using kinematics, then you could get delta x for the second stage. How can I get the total delta x? Okay. How do I get the total distance then? Delta x total is delta x1 plus delta x2, right? But what's the total distance traveled? It's not that.
The absolute value.
You got to absolute value that crap because one of them is going to be negative because one of them's on the way down. Don't you love physics? Get out of here. So finish this problem up after class and you'll see. All right, we'll pick it up next time. We'll probably start moving a little faster there. Sneaky, right? All the pieces that we did today kind of culminate in this problem. So I would do this problem before it gets away from you. Try and do that in the next day. All the definitions, all those tricky things that we did with that whole table, the whole point was so that you would understand what I just said right now. Hope that worked, and if not, well, I guess I got paid anyway, so it's cool. I'm trying to make a joke, but it never works with the mask on. All right. Thank you for the hard work. Jules, thanks. Everybody, let's give Jules a round of applause. Thanks, Jules. And Dom, I guess we can clap for him too.